Hi everyone, and welcome back to Biology 206. I'm Dr. Jennifer Baltzer, and today we're going to be talking about the last little bit of chapter 11, which is focused on life tables, okay? And so this is expanding on our conversations about population dynamics and changes in abundance of population through time. And in this case, what we want to be able to do is develop some tools to project population dynamics into the future. Okay, so just as a reminder, we have four key components of population dynamics, of predicting population abundance. Specifically, this is birth, immigration, death, and immigration are our abide factors, okay? And in previous lectures, I think I've referred to death as mortality, so same thing. All right, so some assumptions so far when we've been calculating rates of population growth is that all individuals in a population are the same in terms of their birth and death rates. And this is not really a realistic assumption, right? So we can think about examples, and here we have an example of elephant seals, where we know that there's a strong advantage for the largest, most aggressive males to be contributing most to the next generation in terms of their genetic contributions, right? And the same thing can be said for various female attributes in terms of their attractiveness to a male in the population, or their ability to survive, their ability to produce large number, or either high quality or large numbers of offspring, all of these kinds of things. So there are differences in that we see in terms of age, size, and sex that can all determine population growth and how population dynamics are changing through time. And the other piece to recognize is that, just returning to some of these ideas that we saw when we were talking about different life history strategies, that there are different types of survivorship curves and different ways that populations can change through time. And so if you think back to our RNK selection, RNK selected life history strategies, here we have our K-selected life history strategy, where you have a high proportion of juveniles surviving through to old age. And this is characterized here by this Dall mountain sheep population. So most Dall sheep will survive to an old age. This is the case for many species where there's a lot of parental investment in raising the offspring, and where there's not a large number of offspring, if you remember that K-selected strategy. And then we have our R-selected strategy, or in this case our type 3 survivorship curve, where most individuals die when they're young. And so this is species that produce a large number of offspring, and many of those die. And we see here this in Balanus glandula, another barnacle species, where, you know, a huge number of juveniles are produced, and that if you think about those species, that'll be a planktonic stage that gets dispersed into the ocean, and very few of those will reach 1 year of age. And so I know, because we're going to be talking about this population in a moment, that only 62 out of a million offspring produced, only 62 of those reach 1 year of age. So a really rapid reduction in population size from one time interval to the next. And so again, these are great examples of differences between species in terms of the age, differences between ages within a population in terms of their survivorship. And then you have some populations, and this is our type 2 survivorship curve, where individuals really just face a constant risk of mortality at all ages. And in this case, song thrushes are an example of that. So this is where, you know, you're equally likely to die when you're young as when you're older. And there can be kind of everything in between these different types of curves, right? Okay, so we have differences. We know that we have differences between ages, genders, stages of individuals at different stages in their development, for example, that impact the survivorship and also impact the fecundity. So there's lots of examples where, you know, the reproductive output increases or modifies with age. So maybe it'll increase with age to a certain point and then decrease with age after that point. So we know that age plays an important role in reproductive output, for example, as well as in survivorship. So these two key factors that go into our calculation of population abundance are strongly modified by these different these different factors, age, sex, etc. And so the way we can capture this is using something we refer to as life tables. And this is a really important tool in the population ecology toolkit. These life tables provide a summary of how survival and reproductive rates vary with age, size, or life stage of individuals within a population. And so if you know, in the example we saw in the previous slide, we've got a number of ages and we know how many individuals survive from one age to the next. This gives us an age-specific survivorship. We can do the same thing for stages, and I'll show you an example of that. And this is really important for population projections. If we know the transitions from one stage or age to the next, then we can forecast what that population will look like into the future. And it's also really critical for understanding how populations may respond to different disturbances, whether it's harvesting, whether it's habitat fragmentation, etc. Understanding which portions of which stages and which transitions that disturbance may act upon allows us to evaluate the implications of that disturbance for population growth. Okay, and so there are two main types of ways that we can describe the structure of populations for life history, for life tables, and one of these is through age-structured. It is age-structured populations. The other is stage-structured populations. The main difference between the two is in one, you know the ages of the population, and so you can model or you can characterize the transitions from one age to the next. In stage-structured populations, you have organisms that the age is difficult to discern, or where stages are just more appropriate to characterize, or where transition from one stage to the next is not associated with age, and so it's more relevant to characterize the transitions between stages rather than ages, okay? And so in age-structured populations, we have an age class, so members of a population whose ages fall within a specified range. And so we can see this here for a population in Nigeria and one in Japan. And we have these different bars that correspond. So we have population in millions on the x-axis, and we have ages on the y-axis. So each of these bars corresponds to an age bracket, and then they've been broken down into another important attribute. And so all the blue bars are pre-reproductive, so juvenile. All of the green bars are within the reproductive age class, and all of the orange bars are within the age class beyond which reproduction typically occurs for males or is possible for females. Okay, and so on the one side we have males, on the other side we have females, and we have two very, very different age structures in these two populations. On the one hand, we have the Nigerian population where it's very skewed toward larger numbers of younger age classes, and there are very few older people in the population compared to this population in Japan, where there's a much higher proportion of the population that falls into these older categories, and a much smaller proportion of the population that is in the reproductive age class or juvenile age classes. And so when you think about the birth and death rates within those population, that really strongly influences what birth and death rates will look like in these two populations. So you can imagine here where we have a much larger reproductive age class, that you'll have a much higher proportion of births, and this is reflected in this this larger proportion of the population being juvenile. In contrast, in the Japanese population, because we have a fairly small proportion of the population in the reproductive ages, we we have fewer juveniles entering the population, and that will only become exacerbated as this very small cohort of juveniles moves into that reproductive category. In contrast, we have a lot of older people in the population, and so we expect that the death rate in that population will be much higher compared to here in Nigeria, where the population is lower. And so these populations reflect very, very different growth rates. On the one hand, we have rapid positive growth in Nigeria, and on the other hand, we have negative growth or a decline in population size in the Japanese population, as you can see from this sort of higher numbers up here and lower numbers down here. Okay, so this is age structuring. And we often use age structuring to model animal demographics. Ages tend to be much more closely reflective of different stages of relevance in animal populations compared to plant populations. And I'm going to give you an example of a size structured or stage structured population. And these are used when birth and death correlate poorly with age. And so if we think about plants, for example, a lot of times it takes, if resource conditions are good, you may have an individual that reaches reproductive maturity or some size threshold for becoming reproductive much earlier than if resource conditions are bad, for example. And so age may not necessarily correspond well with these different milestones that are relevant to predicting births and deaths and consequently growth dynamics in the population. Or it can be used in cases where age is difficult to measure, and so there are certainly going to be some, lots of animal taxa where that's the case as well, where you aren't necessarily following individuals from birth onward. Okay, and so I'm going to give an example of some of my own work, and this is from when I was your age. I was an undergraduate student at Capita University, working on beautiful salt marshes in the Maritimes. Okay. And the plant I was looking at is this species here, Limonium Carolinianum. It's sea lavender. Has these beautiful tiny little purple flowers, and it forms these little these clumps of plants on the salt marsh. And this may look familiar to you because the flowers from this species are used for dried floral arrangements. Okay, and so there's pretty extensive harvesting of these populations, within these populations on salt marshes on the East Coast. And so there was a concern about the sustainability of that floral harvest, the harvesting of entire flower stalks from these individuals, and what that meant for the population dynamics. Okay? But the challenging thing about these plants is that they produce all kinds of vegetative, they reproduce both sexually, they produce seeds, but they also reproduce asexually. They produce ramets that that allow the plant to grow larger and larger. And so you get these very large individuals with lots of ramets that are much older, but we don't know the age, much older and produce more and are reproductively contributing much more to the population than smaller individuals. And you can see a small individual there in that patch that are younger and have fewer ramets. And so there's some stage structuring that's really important, and it's really difficult to characterize, impossible to characterize the age of these. So we used a stage structured population model. And here's some examples of stage-specific characteristics. And so we have survivorship here on the x-axis, and these different categories, so based on the number of ramets, so how large the plant was. So we have seed, the survivorship of seed, how many of them actually survive, are not consumed, don't get washed away, so this is a tidal area. We have seedlings, juveniles, so this is the transition after seedlings where they're small and they're not reproductive yet. And then we have reproductive individuals of different sizes, okay? And we monitored these over a number of years to be able to actually characterize the transitions from one stage to another. Okay, this is an important part of life history, of life tables, is being able to quantify that transition from, seed to seedling, from seedling to juvenile, etc. And so we can see the survivorship at different stages, lowest survivorship at seeds and highest survivorship in these larger plants, 8+ and 5 to 7 ramet plants. And here is some additional stage-specific fecundity, so number of seeds, and proportion flowering by stage. Okay, so these larger individuals are almost always flowering. Smaller individuals, it's a lot more variable. The number of seeds produced increases through these reproductive categories. So all of these are important variables for us to know, okay, well, how are these different sizes of plants impacting reproductive rates, and how what do these different stages look like in terms of survivorship? So births and deaths, these are the two key components. We'll come back to this, but this is just an example of how you would structure this, not structure a life table, not by age, but by stage. Okay, and so what I was just talking about, where we monitor the trend, where we monitor populations through time to actually be able to quantify transitions from one stage or age to the next. Sometimes this is referred to as a cohort life table. And in this case, when we're talking about a strict cohort life table, you start with a cohort, so individuals that have been born at one time, and you follow them through time until they have all died. Okay, so you are actually able to, within that cohort, determine all of the transitions from one stage to the next. So in this case, we have a number of pieces in this table. This is from your text. This is for Balanus glandula. So if you recall, we had this graph from the survivorship curves, and this is, if you recall, this is a type 3 survivorship curve, okay, where we have large numbers of offspring produced, but high mortality in those offspring initially. And we see this in this life table. So if we have 1 million individuals produced in time period 1, only 62 of those survive. And then as we go down through these ages, so we start with a population, this is the cohort that was born at time 0, age 0, and then we move through these different ages over the course of 8 years and look at the number of individuals that survive from 1 year to the next, the number of offspring that they produce, and this gives us a lot of information about survivorship and about fecundity, and then ultimately about that intrinsic rate of growth that we learned about in the last lecture. Okay, so this information that we have in these columns gives us a lot of information both about survivorship and about fecundity. So survivorship being the proportion of the population that survives from one time period to the next, fecundity being about their reproductive output, okay? And in this case we have, for example, at age 0 we have 1 million individuals. At age 1 we only have 62 individuals. We can use that information to calculate survivorship, which is n at time x. So in this case, x is 1. So the number of individuals surviving at time 1 divided by the number of individuals at time 0. And so we can see that survivorship, it's very, very low. This is why we see this massive drop here. It's 0.000062. So 62 over 1 million, okay? And not surprisingly, as we move up through our different categories, we have changes in that survivorship, okay? And so we can then use the same calculation to look at survivorship across all of these time intervals. So this is where our survivorship our survivorship from one time period to the next is the lowest, but because we compare this number always back to that original time 0 number population size, these numbers get lower as we move through time, but stabilize quite quickly, as you can see, okay? So that's survivorship. This is LX is the term that we use to reflect survivorship. And then fecundity is FX, and this is the mean number of offspring per adult. And so in the case of this age X, there's no offspring produced, and so our fecundity is X, and this whole row is kind of doesn't provide us any information aside from the initial population size. But in time 1, we have 62 individuals. They produce an incredible 285,200 offspring, okay? And so we can divide number of offspring by the number of adults and get the fecundity, which is 4,600. So that's the number of offspring produced per adult on average. And we know that different adults may produce different numbers of offspring, and that's a different component to, that's something different to think about in here. But what this lets us do is across different age classes, look at the changes in fecundity. And so you can see as we move through time that right around age 4, these barnacles start to stabilize in terms of their fecundity. So they reach their maximum fecundity at age 4, which is 12,700 individuals per adult. Okay. Then we can estimate per capita growth rate. So if we multiply survivorship and fecundity and sum those all up, so we get an IX times FX value, and if you sum up everything in this column, we get the per capita growth rate, which is RO. And so that's the sum of LX times FX, which in this case is 1.27. Another component we can calculate from this table is the generation time, which is the average age of parents of all offspring, okay? And so the way we do this is we take this term, IX times FX, we multiply it by the age. We do that for every single row within the life table, and then we can sum these up divide it by the net reproductive rate to give us the generation time, okay? So again, that's the average age of parents of all offspring. Okay, so then finally, we can take the natural log of RO, our net reproductive rate, divided by generation time to get the intrinsic rate of increase, which is that R value that we learned about in our last lecture. And in this case, it's 0.08. And if you recall, an R value higher than 1 indicates that the population is growing, and R value less than 1 indicates that the population is declining. So this population of barnacles is growing, is growing at a rate of 0.08. So this is the kind of information we get from life tables. It's really critical for forecasting. So you can imagine if you said, okay, well, we're going to harvest, for whatever reason, barnacles ages 5 through 8 are going to be harvested, and we remove this portion of our age classes. The implications of that for net reproductive rate and generation time would be pretty large, because it would modify those numbers, those sums of this column and this column, which determine those values, and ultimately that would modify our intrinsic rate of increase and probably lead to a population that was declining, because these are the ages that are reproducing kind of at their maximal level. Okay. And so this is just an example. We talked about the fact that information from life tables can be used to forecast population dynamics. And this is just an example from that paper I was mentioning that was from my own undergraduate thesis research, where we did just that. And this is a little fuzzy. I can provide you guys with the paper if you want. But you can see that these, when you draw these out into diagrams, they look pretty complex for stage structured populations in particular, because you could have movement between a return to the same stage, or a movement from one stage to the next, or a return from a larger stage to a smaller stage because a rammet died or whatever it happens to be. So there's a lot of different arrows that we have to parameterize in this, and each of these numbers represents a transition from a transition probability from one category to the next, okay? So we see that the transition from seed to seedling is only 0.035. From seedling to juvenile, it's much higher, it's 0.233, and then it drops down again for a juvenile to reach reproductive maturity, okay? And we have return of juveniles to the juvenile stage, because it takes a long time for individuals of this plant species to become reproductive. So when we have this kind of model parameterized like this, then we can play around. So in this case, we were interested in the harvesting of flower stalks and what the implications of that were for population size. So we could manipulate harvest and say, okay, we're going to harvest 30%, 60%, 90% of flower stalks. And what that did was reduce these transitions that feed into the seed category by that proportion. Okay, so we reduced the transition, the adult, the reproductive transition, the reproductive output transitions, by these amounts and looked at the implications for population dynamics. And we see that at 30% harvest, the population is more or less stable. But once you get to 60% harvest, we start to see rapid declines in the population. And the reason for this is because it takes so long for juveniles to become reproductive. And if we don't have that input of new juveniles into the population, all of a sudden that population it lags and then it crashes. Okay, so these are the kinds of forecasts we can make with population dynamic, with life tables, and with these kind of stage or age structured population models. Okay. And that, I just wanted to wrap up that chapter with this short lecture. We will be moving on next to our chapters on biotic interactions, so predation, competition, and mutualism. And don't forget that this Thursday we have a special guest lecture. So we have the second visiting scientist speaker, Dr. Frances Stewart, will be coming to talk about some of her work with martens in Western Canada. So please join us for that synchronous session on Thursday evening at 5:30, and I will hopefully see you tomorrow night at student hours. Have a great night.